That's what made it worse. Not that I know of. So I'm like, there's a problem. Either my shoes are squeaky or something's going on. I don't know. Wow. All right. Yes, this is now being recorded. Oops. But you don't need this one because that's the wrong year. Or that's the wrong thing. Okay, here we go. Yes, it is. All right, that's great. Oh wow, guys. Okay, here we go. So pretty straightforward. Plot them. Notice the best fit line, right? Just a straight line through there. Obviously, don't connect the dots. Okay, that's. You're laughing, but I've seen it. I've been a grader. I see what people do. Okay, so that's like 2 free points, right? Then it says use the best fit line you sketch to determine experimental value for the spring constant K. So if you do weight, which is force, right, rise per length, that's like K, right? Because K is newtons per meter. Does this make sense to you?
So basically just find the slope.
Find the slope. And here's the other thing. This is where they're testing to see if you know what to do. Because note, like what a lot of people do is they will use the points. Do not use the points. Do not use the data points unless what?
It touches the line.
Yeah, and I kid you not. They will look in the tiniest of degrees. So do you see that right there? You see the little white in between? Right? See that little tiny berry of white? If you use that dot, you're wrong. That dot literally must be on the line.
That dot has to be on the line?
No, that dot doesn't have to be. Yeah, you must use dots that are on the line. And if they're as close as that, and you use it, you're wrong. You have to use dots that are on the line. So, just pick this one and that one, because they're easy. You get it? Pick points on the line. Do not pick data. You want a simple rule? Never use your data points. Okay, seriously, it's a simple rule. Never use your data points. Just draw your best fit line, pick 2 dots on that best fit line, and move on. Right? And you want to know the simple way, the thing to do there? Always make sure that you draw a line that goes through at least 2 of the things so that you can pick it easy. All right? And there, of course, is your delta y. Here is your delta x. And, of course, your slope is just rise over rho. Yeah, it was asking for k, right?
Yeah.
Yeah, and k is just f over m, whatever, f over x, yeah. Because you know Hooke's law, this is f is negative kx?
Yeah.
Yeah. So you're just using, if f is negative kx, then k is f over x.
So it doesn't matter if it's negative or not?
No. The negative is simply so that you know which way to draw the vector. Okay, here we go. Back to this. Okay, so we've done that. Oh, wait, I can show you here. Yeah, here we've done that. See? Right? Look, the slope is used, so you have to show that, right? And then the calculation for the 2 points using the straight line from the straight line, right? Not from your data. And then notice, usually they have a thing on the bottom that says about making sure the grader knows that you're not supposed to use points that aren't on the line. Okay, questions from this? Yeah.
I found this is it's negative k delta s, right?
Yeah.
So how does delta s go to
Oh, because you use delta s, x, same thing.
But I mean, those are different units, though, aren't there?
Huh?
Isn't that different units?
What's that?
Well, what units is Hooke's law use?
What units is, oh, newtons and meters.
Yeah, and doesn't that length and weight?
Yeah, weight is in newtons.
Oh.
Yeah, that's the sneaky part. It's not mass, it's weight, and weight is in newtons. But good questions. Very good. All right, everybody cool with the first parts? First A and B? All right, so then we go here. Now we get the bungee jumping problem. Okay, so yeah, this is still 3, or whatever, the same problem. So this gets dropped, right? So the student attached the object, blah, 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 holds the object to use the point, blah, blah, blah. When the object is released from rest, it falls 1.5 meters before stopping and turning around. Assume the air resistance is negligible. So they're saying the total stretch plus the original length is 1.5 meters. Calculate the value of the unknown mass m of the object. Yeah, well, at that point, you can do, if you want the mass, I think you could just do energy. Because at the maximum stretch, if you use the bottom of the stretch point as 0, then your, do we know the original length of the rope? I don't remember. Let's see. They'll show us here. Oh yeah, okay. Yeah, just use energy. Using the bottom as the as 0, then you can say mg y max is 1/2 kx squared. And then, oh yeah, y max is 1.5. Correct substitution x. Okay, I guess x was from the previous part where we learned how long the string or rubber band or whatever the heck it is. We saw that in the earlier part, so because we know that, we can get the stretch. Okay, and then just plug everything in. So you just use the parts A and B to know the original length, and subtract that from the 1.5, and you'll get it. Questions?
Wait, what does delta S mean?
Delta S is just delta X.
Oh, okay.
S, L, R, X, H, Y, Z, those are all just distances or displacements. Well, technically delta is a displacement. Those are all measurements of position or length. Okay, any questions on that part? Any questions on part C?
So basically it's an energy problem, but
Yeah, it's just energy problem, because here, see this?
uh-huh.
They told us the length, 0.6 meters, because there was no weight on it, it's 0.6 meters. So then, if I tell you that it goes down 1.5 meters, you know that the stretch is 0.9 meters, right? So that means I can figure out everything, because I know the x, blah, blah, blah. All right, then, oh, sorry, yes.
Can you explain the energy change?
Sure.
When it went from top to the bottom?
So what we're doing is we're saying, oh, let me move this down a bit. Am I recording this? I think I am, right? Yeah, okay. We're saying this goes down to 1.5 meters. We know the original length is 0.6 meters. So that means, although this is not to scale, that means the delta x for the stretch is 0.9 meters. Okay? So we know that the PE at the top is going to equal the PE at the bottom. Right, the initial potential, or if you just say mechanical energy at the top equals mechanical energy down here, what kind of energy does it have here? It's just going to be mgh, and this is going to be 1/2 kx squared. And then our h is 1.5 meters, our x is 0.9 meters. Oh, we're good.
Wait, where did the 1/2 square come from?
That's a potential energy in a spring. What's that? Isn't it a what? Yeah. Elastic.
So basically it's mgh equals 1/2 kx
Nope.
squared.
Because have you ever been on a bungee? Have you been bungee jumping? Yeah.
That's so weird.
You know how like have you ever done where they set it up so that like you're over a river? You ever do that one? Yeah, your head goes underwater. Yeah, you go down underwater because the potential energy that you had is enough to stretch it out down into the water. But then your weight versus the force in the spring causes you to have an equilibrium position that's above the water. So it's not like you stop and you're underwater. Right? It's like you go down, you go in the water, then you come back up, and then eventually you stop above the water and they crank you back up.
They want to go to the
I don't know, maybe it was hot. Did you ever see the joke that they did on YouTube where this guy is like jumping off and they make him face backwards, right? And no, he's facing forwards and he's like diving. And they're like, 1, 2, 3, and he jumps and they have an extra bungee cord. And when he jumps, they throw the bungee cord after him. Right? It's like you're flying off. Yay, this is fun. Hey, that's my bungee cord. Does that work?
Wait. So he doesn't have. No, he does.
He does. There's an extra one, but they throw it after him, so it looks like his bungee cord came off while he was in the air.
Sucks, dude. This is a troll movie.
I'd be like, all right, I'm gonna make sure I just go head first into the ground because I don't want to like go sideways and then like lay there for like an hour before I die because you have to like climb down the cliff to come get me. No. All right. So part D, calculate how far the object has fallen at the moment it attains maximum speed. Remember this? This one is our friend.
Calculate how far.
This is just like that spring problem on the incline. Remember that? And as Josh reminded us, this occurs when the sum of the forces is 0. So all you have to do is do the force statement that gives you the sum of the forces are 0, and then you should be able to find it. Oops. So if we take a look at, oh, is it this one? Oh, it is this one. Okay. Yeah. So wait, is this right? No, this is the old one. Oh, this is 07. That's why nothing matches. I thought I had. Oh wait, there we go. Oh, okay. Here we go. So yeah, see, sum of the forces is 0. That's where it's occurring. So then we say mg is kx. Boom, 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 boom. Get our answer. Done.
Oh, wait, KX is the force.
Yes, that is of Hooke's law. Yes.
And then MG is just.
Yeah. 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 The other one. Oh yeah. So calculate how far down the object has fallen at the moment it attains maximum speed. And remember the weird thing that we said is when you start falling, when the bungee cord or the rope or whatever starts pulling back on you, at that moment, that doesn't mean you stop accelerating. It just means you accelerate less. And as the tension in the rope increases, then that force starts to cut down on your acceleration until the spring force is equal to the force of gravity. At that point, that's when you'll be at your maximum speed because you were accelerating all the way to that point. After that point, now you will have a net acceleration upward and begin slowing down until you ultimately stop at 1.5 meters and then bounce back up.
Are you recording?
Yes.
Acceleration again?
Maximum acceleration?
Wait, no, there. What?
Maximum velocity.
Yeah. Okay.
Okay? When the sum of the forces are 0. Because if you think about when is velocity, when are you going to stop having a velocity? Like when is your velocity going to start going down? Only when someone accelerates you back up, right? I'm sorry, let me say. When is your downward velocity going to begin reducing in magnitude, meaning getting smaller? Only when you have a net acceleration upward. And that won't happen until the force of the spring or the elastic force overcomes gravity. Okay? All right. So is everybody cool? Is everybody cool with DI?
So DI is just basically set all forces equal to 0. And
That's
then
it.
use
Sum of the
Hooke's
forces
law,
is 0. Solve for x. That's it.
And use Hooke's law.
Yep. Explain why this is the point at which the object has maximum speed. Just do what I just said. Basically, you just say that every point up until this point, that object is accelerating downward. There is a net acceleration downward. And then after this point, there will be a net acceleration upward, which means the velocity will decrease. That's probably the simplest way, I guess, that I can think of. So before this point, there's a net acceleration downward, so my velocity is increasing. After this point, there's a net acceleration upward, which will decrease my velocity and therefore make that the maximum. Let's see what they said. Here we go. Okay, so yeah. Acceleration is 0, blah, 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 whatever, bunch of crap.
Hi.
Hey, how you doing?
Janice.
Oh, good, thank you.
Are they here?
Catherine, Bung, and May. Yes, they are.
Okay.
Yeah, good. Alrighty then. So let's proceed to the last piece. Calculate the maximum speed of the object. Well, I mean, you know how far down it fell. You can, you can do energy at that point if you wanted to. That would work, either one. And that's what they did. So we know where that point occurs, right? The point at which maximum velocity occurs. We know the distance because we calculated it in part I. So just plug it in for the energy statement. Good God, what is this? It's like a million things. We just need to figure out a way to give everybody like little digital, I don't know, iPod touches or something when you're freshmen, and you just got to use them before you're
Give everybody a pager.
a pager. Oh my God. All right, any questions with this one? Does this make sense? This is just energy, right? Here, remember, this is our potential energy in the beginning. Okay, and this is what, it looks like what they did was, this point is not at 1.5, right? It's above that. So what they're doing is they're saying the point at which maximum velocity occurs is 0. And then they're taking the potential energy as the height above that, right? That's what YV max, that's why they wrote that. So they're saying that potential energy equals some amount of stretch, because this has some stretch, right? It has to have enough stretch so that the force of the spring, or the elastic force, is equal to gravity. We calculated that already. We don't have to do anything new. It's part I. And then Vmax is what we're looking for. So plug it all in, solve for V, boom, done. Okay? And of course, that stuff is all online for your perusal. Any questions? Yes?